Yes.
Okay. So let us start with the self-organizing map. We have seen the clustering algorithm. So clustering is about finding the similarity in the from a given data set. So that is, it's a form of, it's a type of unsupervised learning. So now you have seen the k-means clustering, and so what happens? The k-mean clustering is that we are finding a centroid, then we are calculating the distance measure, we are updating the centroid, we are iterating that process, and then finally, when two successive iterations doesn't produce much change, then we are freezing on that particular combination, and then we are taking it, we are forming the clusters likewise. But the problem with k-means is that first of all, we need a k. So we don't know from a given data set how many clusters are there, whether it is 1 cluster, 2 cluster, 3 clusters, we don't know. So we need a k. That is one of the thing. And if you have an outlier, then that is again another drawback, because it keeps on oscillating. So finally, the k-means, we have to finalize the clusters based on finalize the groups based on the consecutive iterations, and whether there is a change is happening or not. So if there are outliers, it keeps on oscillating between one group to the another. So we are not able to finalize the exact groups. And then another thing is that k-means does a hard clustering. So these are the drawbacks. That is which is the exact reason why we are going for dynamic clustering algorithms. And self-organizing map is one such algorithm. So what self-organizing map, unlike the artificial the neural network approach, it is based on like a neural network that is based on the back propagation. The self-organizing map is based on the competitive learning. I don't know why this is keep on. Yeah, so this is how the another important aspect of self-organizing map is that if we have a high dimensional data, it is that high dimensional data is being projected into a low dimensional lattice. So we are converting an input data vector that is high dimensional into a low dimensional lattice. So let us see that in the figure that is displayed on the screen. X1, X2. Oh, the slides keep on. Okay, one second.
Sir, you can try and remove, see, in the slide shows, remove the timings.
Okay. Okay. Yeah. Thank you. Oh, let me see whether it is a mouse problem. 1 second. Yeah. So we have an input vector, and the input, that is a high dimensional input. That is a very complex input. And then we want to have a better visualization of the data, input data. And then we are for that we are projecting that into a two-dimensional lattice. So here the input vector is x1 to xn. So it is there are n features. It is an n-dimensional vector that we are projecting onto a two-dimensional lattice. So this, how do we project that one? For that, each of the output node, the two-dimensional lattice, each of the element of the two-dimensional lattice is represented by a neuron. We call lattice, or it is a processing unit or a neuron. So each of these neurons is connected to different different vector elements x1 to xn by means of synaptic weights. So that there is a weight matrix that is coming in picture in between. So like every other learning, there is a training process involved. So what is the first thing is that we have to initialize the neural network weights. So the weight initialization is the first part. So how do we initialize it? So at first we will choose random weights. So randomly select the weights. Then we have to have a we have to, it is based on the self-organizing map is based on the competitive learning approach. So we have to calculate a discriminant function. How do we calculate that? How do we and maximize the discriminant function? So maximizing the discriminant function, here how we do is that we will minimize the Euclidean distance. We will calculate the Euclidean distance, and then we will find which of the neuron is closest to the input. So finding the minimum distance. So that is the next step. And once the minimum distance is found, that is the winning neuron. That is declared as a winning neuron. So once the winning neuron is found, then the next step is to update the neuron weights. And then again, iterate the same process until the weight vector is stabilized. So we can see that here there is a 3-dimensional data consisting of the input are x1, x2, x3, and we are mapping onto the neurons w1, w2, w3. So these are the output nodes, and x1, x2, x3 are my input nodes. So now it is calculation of the discriminant function. So d1, d2, d3 we are calculating. How do we calculate d1? We are calculating the Euclidean distance, and the Euclidean distance is calculated. Now see, x1, x2, x3 we are so the highlighted one, x1, x2, x3 are 0.5, 0.3 and 0.7. So while calculating the Euclidean distance, it is under root for d1 it is under root 0.1. It is a summation of I equal to 1 to 3. I equal to 1 to 3 is the number of vector elements, and xi minus w1 comma I the whole square. So it is under root. So this is the first element is 0.5, and what is the random weight associated with it? It is 5. So 0.5 minus 5 whole square, 0.3 minus 13 whole square, and 0.7 minus 20 whole square. So this is for W1. Let me. So these are the weights 5, 13, and 20. So, and these are the inputs 0.5, 0.3, and 0.7. So that is why we are 0.5 minus 5, 0.3 minus 13, 0.7 minus 20. So we calculate this distance, that is coming out to be 23.5. Similarly, we calculate the distance for the second neuron, and that is again using the same formula. Now it is 0.5 minus 14. So the weight here is 14. The next weight is 7, and the next weight is 3. So we calculated 15.2 we get, and for D3 we get similar approach, we will get 31.6. So now so this is the winning neuron. So the D2 is the winning neuron. The second neuron is the winning neuron. So we select that as the winning neuron, and the next step what is so winning neuron is selected, and the next step is updating the weights. How do we update the weights? So it is we have to find the change in weights. The change in weight is calculated by eta t into tj ix of t into xi minus wji. So this formula looks a little bit complicated, the weight updation formula, but we will break down that in the next slide. So t is the topological neighborhood. I of x is the input. So I of x is the index of the winning neuron, and then t is, now this is a function of time. So in the next slide, so this is the weight, the change in weight. So eta t into tj comma I of x. I of x is the index of the winning neuron, and j is any other neuron, other neuron. I is one neuron, and yeah, here right side the definitions are given. T is the epoch, and I of x is the winning neuron, and then there are hyperparameters associated with it, and that is eta naught, tau eta, and sigma and tau naught. So the weight updation is calculated here. So now eta t is the learning rate. That learning rate is not a static learning rate. As the epochs are increasing, we are altering the learning rate. So the learning rate keeps on changing with as a function of time, and it is defined as eta naught into exponential minus t by eta. so that the how it is dependent on time, it is exponentially dependent on time, that is given, and then the topological neighborhood. So the competition process is now, so far we by calculating the distance formula, we looked at the competition process. Now this SOM updation, it is not only consisting of competition. The first is competition, then we have a collaboration that is coming, collaboration or cooperation. So what is collaboration or cooperation? uh, we have a neuron here. Let us say this is, so we identified the winning neuron. So this is the winning neuron that we identified. But now we should have the this synaptic updation works in the using the principle of Hebbian rule. So Hebbian rule, what it states is that the neurons that fire together wire together. So once you identify the winning neuron, we have to find the influence of the neighboring neurons. So whichever is the winning neuron, the neurons close to it will be more excited compared to the neuron that is farther away. So we will define a radius, and in this radius, whatever neuron is coming, that will have a higher synaptic strength. So the one which is in the center will be having the very high synaptic strength, high strength, and then that strength fades away as we move away from the center. So which function will accurately can best describe this particular phenomena? So that is best described by the Gaussian function. The simplest function is Gaussian. So Gaussian, what it is? So as the distance is zero, the strength is very high, and as the distance keep on varying, moving farther away, the strength keeps on decreasing. So that is why we are the topological neighborhood. We can see that we are using a the I of x is the how far it is from the winning neuron. So and then as a function of time. So we are defining a uh, uh, defining the neighborhood using a Gaussian function here. And now what is that exponential of Sji of x divided by 2 sigma t. So sigma is, so this is 2 sigma. So this is, so this is 2 sigma. And what is Sji x? So Sji is the lateral distance between the neuron. So Sji is it is calculated by modulus of Wj minus Wi, where the index j is one neuron and index I is the another neuron. And then sigma t is defined it is again time dependent, that is exponential of time divided by the tau naught, and that is a constant. So this is how the weight updation rule will work out to be. So now I will now I think it is still difficult to visualize what is how the input is mapped to the output. Before going to that one, we will try to solve a simple simple problem so that you the understanding is much more better. So I will open the board. So I hope this board is visible to everyone. So this is a very simple example. In the real time, the problem will not be as simple as this, but for the sake of I'm taking a very simple example. So let us consider four given vectors. The vector 1 is 0, 0, 1, 1. Vector 2 is let us take it as 1, 0. So this is the third vector, and then another input, the fourth input vector is I see only 8 people joined the board, but I hope the screen is visible to all of you.
Sir, I don't have access to join.
Yeah. So this one, no, in the chat box you will get a link for the chat.
No, after clicking that link, I'm getting that I don't have the access to join.
Access. Okay, okay, fine. So I. Oh, okay. You can send a request. Can you send a request? I think to access. Then I think I will get a request probably. Otherwise, you are able to see the screen. No, I am anyway sharing the screen, so you are able to see the whiteboard, right?
Yes, sir.
Okay, okay. So let us continue this way because I think there are 60 people. So if everyone sends a request, then manually, ideally it should have sent the request to everyone, like access to everyone. But I don't know what happened. So these are the two. We already seen an learning rate. So for simplicity, we will assume the learning rate as 0.5. We are not considering it as time varying. In actual, it is time varying. So now we have to construct a SOM. So there are two types of SOM, but we will be using the Cohen self-organizing map. That is mapping the higher dimensional input into a one or two dimensional lattice. So initial learning is 0.5, and the we have to construct the self-organizing map. So how do we go about it? So as we discussed, the first point is we have to initialize the weight, and let us assume clusters is equal to 2. So here we are considering only 2 neurons. And the dimension of our input data is 4 because for each x is represented by 4 vector elements. So how do we now all this data has to map into the output. Similarly, this is mapped to the second neuron. So this is the second output neuron. So now this is neuron 1, this is neuron 2. So now this is the input. And so we have the weights defined, etc. We have W42 here. So the first one is, let us randomly initialize the weight. There are two clusters and then four elements, four vector elements. So it will be a 4x2 weight vector. So let us define the weight vector. Let us randomly give 0.2, 0.4, so we will select the weight between 0 and 1. And let this be odd numbers like 0.9, 0.7, 0.5, and 0.3. So first, let us take the first input vector. What is the first input vector? We have 0, 0, 1, 1. So we are required to calculate D1 and D2. So what is D1? It is summation Wij minus x1. This is the first input vector. So the whole square. So this is nothing but the first one is 0.2 minus 0. So 0.2 minus 0, the whole square, plus 0.4 minus 0, the whole square, 0.6 minus the third vector element is 1. So we will square, plus 0.8 minus 1, the whole square. So I'll write it here. So it will be 0.2, the whole square is 0.04, plus 0.16. The third element also is 0.16 minus 0.4, the whole square, plus again it is 0.8 minus 1 is minus 0.2, and then it is 0.04. It will total out to be 0.4. So this is D1. Now we will calculate D2. So D2 again, it will be the vector is 0, 0, 1, 1. And the weights are 0.9, 0.7, 0.5, and 0.3. If we calculate that one, it will be 0 minus 0.9. The 0.9 minus 0, it is 0.9 square, plus 0.7 square, and then this is 0.5 minus 1 is minus 0.5. Then this is again 0.25, and 0.3 minus 1, it is 0.7 square, it is 0.49. So 0.81 plus 0.98, so it is 1.79, and it will be 2.04. So now we have to see, we calculated D1 and D2. So which one of that is minimum? So D1 is minimum because D1 is having 0.4. We saw it here. D1 is 0.4. So D1 is the winning neuron. So once we select the winning neuron, next step is weight updation. So how do we do? We are not taking the neighborhood. We are just updating the weight updation for the winning neuron. So the weight updation, let us first take a simple weight updation formula, but we have to expand it considering the neighborhood. Wij new is equal to Wij old plus alpha of t. So this is the learning rate. And we have xi minus wij. So what is w? Weights we are trying to update is 0.2, 0.4, 0.6, and 0.8. So the first weight will be 0.2 plus alpha. Right now we are not varying it with respect to time, so we are keeping it as fixed 0.5 in this problem. And then what is xi? Xi is 0 minus wij old. So this is old is 0.2. So that will come out to be 0.1. Similarly, this weight will come to be 0.4 plus 0.5 into 0 minus 0.4. This will come to be 0.2. So I know, I will not calculate I will just simply write the weights of the other elements. So this is 0.8, and then this will turn out to be 0.9. D2 weights will not change. So now the new weight vector it will be 0.1, 0.2, 0.8, and finally 0.9. And the other one will be same. There is no change. So 0.7, 0.5, and 0.3. Now, this need to be continued. So we are not confident about the weights still. So let us take the second input vector. What is the second input vector? Second input vector was so the training has to continue for multiple inputs until the weights are showing a similar pattern. So the second input vector is 1, 0, 0. So again, we will calculate do the same approach. We calculate D1 and we calculate D2. We have to calculate this with respect to this weight for D1. we will get 0.1 minus 1 the whole square plus the second vector was 0.2 and then minus term is 0. So and the third term is 0.8 minus 0 and the last term is 0.9. We will get a weight as 1.7 and D2 similar approach we will get it as 0.84. Now this is the winning neuron. So in the next iteration what we do is that we will perform weight updation for D2. Weight updation we will get, so I'll skip the calculations because we will cover the applications also. So for neuron 1 weights are not changed. So neuron 3 weights are, the neuron 2 weights based on the weight updation formula we will calculate it as the new weights will be 0.95. Initially it started with 0.9, 0.7 and all. So now it is changed to 0.95, 0.35, 0.25 and 0.15. So now the same inputs are haven't come to a similar pattern the previous input. So we will go with the third input vector. Again, do the same performance, the same operations. So the third vector was 0, 1, 1, 0. And then we will calculate D1 and D2 using the Euclidean distance. Then we will do weight updation. At the end of the third vector, so we will, based on the distance calculation, we will find that the D1 was the winning neuron. So we update the D1 weights, that point. And the weights for the second neuron is updated. During the last iteration, there was not much change. So these weights will be same. And then we will move on to the next input. The last input that was 0, 0, 0, 1. So we need to keep on training. So after doing that, we will get another weight. So this training need to continue until you find a satisfactory pattern in that the weight vector. So in actual, and normally this is biologically very relevant in the human brain also. It is the synaptic connections are formed in the similar manner. So that happens dynamically. So it happens like if in a phenomena similar to this one only. So so this example I just showed you for a basic understanding how the competition is taking place, and then now here we considered only 2 neurons, but there can be many neurons in the cluster. So we updated here, since we had only 2 neurons, we updated only the D1 and D2, either the weights corresponding to D1 or weights corresponding to D2. So these 2 neurons are, we treated it as exclusive, like totally independent neurons. But in actually, when we form a 2-dimensional lattice, there are neurons that are close by, which is having influence to the central neuron. So we have to take that into consideration as well. So at the end of that, if we find this is the winning neuron, then we have to find the neighborhood, and then define the neighborhood, and then update the weights accordingly. Like the strength decreases as it goes farther from the center. So this concept we have to apply. So now coming back to the slides. So I think we have only 15 minutes left. So I'll come back to the slides, and then now I will what is the relevance of this input vector, and then what is how the mapping. So in order to visualize that, please consider this scenario. So this is the human brain. So the inputs are nothing but, these are the inputs, like speech, what you hear, the smell, you see a face, you want to recognize that particular face, and then the other aspects like the reading, the language, everything is topographically mapped inside the human brain. So that particular, this kind of formation is achieved using the self-organizing map. So how the left side, you can see there is an input layer. So these input layers, x1 to xn, that is nothing but these stimulus that you are receiving, that speech or the sight or the smell or something like that. And then that is, now the weights are nothing but the synaptic connection. Between the neurons, there are synaptic connections involved. Even from that input to there are receptor neurons. The receptor neurons in the first layer. Then as we go deeper and deeper towards the cortex, there are levels of hierarchy coming into picture. So these weights are nothing but the synaptic connection between the neurons. And finally, that the processing unit. So that is the cluster that we are talking about. That is the self-organizing map cluster that we are talking about. So this is the mapping. So this is, you can visualize in this way, what is input and what is the output, how we are mapping. So output, since it is, we are mapping into a 2-dimensional space, that is nothing but the dimensionality reduction. So what are the applications? So this is one of the application, that is to model the biological process like perception, the sense perception and all, we can model using the self-organizing map. Another application is that you have a I think this is sir also already showed this example in the class. We have a massive document collection. There are lots of research papers and patents available, and then out of this database, we want to group that into different categories. So this is belonging to science, this is belonging to maths, this is belonging to history, kind of thing. We want to group it. So that can be achieved using this self-organizing map. So that project is called Websome, that you can, there is already a research paper available in that one. And then the another one, so this is the now clustering the medical topics. Okay, let me see whether I am there. Okay, fine. So clustering the medical topics. So there are in the medical field alone, there are 2 million medical papers. So how do we do it? We process the text, and then a SOM with 75,000 neurons is used. Then after post-processing, we will get the final result. So you can see that in the bottom right, you can see neurons, you can see hippocampus, the action potentials and all. So everything related to the neuroscience, that is getting categorized into the bottom right portion of the screen. And then in the middle top middle, where you can see heart rate, the blood pressure, body mass index. So this is getting categorized into another section. So this is achieved using the self-organizing map. So another explication is the phonetic typewriter. So this is again discussed briefly, touch upon in the class. And you can, there is another problem like calculating the visualizing the poverty, the classifying the world map in terms of the poverty. So the how the poverty is determined is based on different kinds of inputs like economic background, the financial capacity, and then what the natural resources. There could be many parameters that is influencing in finalizing the poverty index. So how do we do that? So that is a very dimensional, high dimensional data. The poverty data kind of thing for a country. What is the agricultural income? What is the educational facilities? All these things add up to determining what is the poverty index. So that is a very high dimensional data. We want to convert it into we can see in the left hand side that is a 2D lattice. The color, the bottom right, the bottom. I will use the. So we can see that this color. This is indicating a poverty index, a different poverty index, and this is indicating this is the well-to-do countries. And there is an overlap also. You can see that this is shaded as a violet color. This is shaded as a green color, and then the cluster in between, there is an overlap between. Some of the features are matching, overlapping in between these two countries, and that is why there is an overlap in color. So that is how the maps are created. To understand better understand how this classification is done, let us look into this example, one example again. Let us see, this is a three-dimensional data. This is x1, x2, x3. So this is a three-dimensional data, and then we are mapping it into a 3x3 neuron. So to better represent it, the three. So this one, we will be mapping it like this to the neuronal cluster. So every neuron will have a connection to the input. So to have a better representation, let us rearrange this 3x3 lattice into a single dimension, that is 9x1. And then all the inputs are mapped to these neurons. And now the next step, what we do is that for each node, we calculate the distance and then find out which is the minimum distance. So this particular neuron is closest to that particular input. So this is having a minimum distance, and this is closest to that input. And the next step, so now for representation, we selected 3x3. Now let the cluster be a little more bigger cluster. So we, based on the minimum distance we find, this is the winning cluster. So the next step, what we need to do is that we need to find the neighborhood. So neighborhood, based on that Gaussian function, the decreasing strength is, if it is close to the center, it is having a higher strength, and as it is moving away from the center, the strength fades. So we define a radius, and the strengths are updated accordingly. And based on the next input, whatever we are getting, there could be a different neuron that is having that is a winning neuron. And again, we form a neighborhood. And then the overlap that which I was talking about is this one actually. So there is an overlap here. These the strength towards this particular input is very less for these neurons and for this neuron also, but there are overlapping. There are certain features that are overlapping. Similarly, we find a new center again we find a new center, and then there are multiple overlapping regions, and finally we if we use a different color for each of these particular centers and then form the neighborhood, we will get something like this. We will be able to map the data into something similar to this. This is the poverty map of the nations in the world. This form. So what we achieved is that, so left side we can see that this is the high dimensional data. So these are the countries, and then this is one of the feature. This is the health condition, the educational parameter, then the inflation rate, and then so on. It's a very high dimensional data. So now all these this very high dimensional data we data into a pictorial form, and then after that we are mapping it into a world map. So this color we are translating it into the world map. So this is our final outcome. So getting this particular data, it is after lot of different processes. So that is achieved using this is one of the application of self-organizing map. So this is and then so basically the self-organizing map, it is clusters into, it groups it into the into different clusters based on the similarity, so that we can see in the left side and the right side figures. So now the Websome project that which was mentioned in the previous slide, so that is this one actually. So it was done in 1996. They classified around 5,000 documents. The mapping was done based on the histogram vectors, and they found the similarity between the words from the documents. They filtered out the words, found the similarity between the words, and then they were able to classify around 70 lakh patent abstracts. So now that's where reducing the dimensionality of the histogram vectors. So that is one of the point, and there are this reducing the dimensionality, that is reducing the histogram vectors, also helps in increasing the computation time, and it doesn't compromise on the classification accuracy. So now this is about the how to find the histogram vector, and this you have to read the paper in detail. There was a Websome 1996 paper is available. You first find the histogram vector based on the words, based on the words used, and assign the weights to that particular words, and calculate the discriminant function, and based on the discriminant function you categorize those words into different groups. Then you after the histogram function is formed, then you reduce the dimensionality. Then once that how to reduce the dimensionality, so that is given here, that is the original dimension is x, and that dimensional d dimension is converted into k dimension, where k is very much lesser than d. So this is the projection formula that is being used. That's a d dimension, that is the input dimension, and then the input that is getting translated for this particular, this was the formula used, projection formula used for this particular project. And yeah, so this is, I don't think we need to go into detail of this thing, just for giving you an idea. This Johnson Lidenstrauss lemma, how does this work? So that is briefly mentioned here. And yeah, so the accuracy is not getting compromised, and then finally we are able to cluster or group the particular large document database into different categories. So that is So yeah, that's I think we are done with the time also. So that is few of the selected applications of self-organizing maps. So maybe you have to practice some problems. So only we for the practice we focus only on the competition part. There is also after competition, the neighborhood formation is one other important aspect, where we define a Gaussian function and then we uh, define the collaboration according to the decreasing Euclidean distance. And then after that, the next step is the weight update. So basically there are three important steps. One is the competition, where we find the discriminant function, select the lowest distance metric. Then the collaborative process, where we use a Gaussian function or a Mexican hat, and then find the neighborhood. And then the last one is updating the weights. And then again this process has to continue until you find a satisfactory weight matrix. So that is all from my side. If you have any questions, then you can let me know. And if